Okay. In this movie clip, let's begin with the base current components. So the topic of this movie clip is how to how to say what kind of current components exist in building up the base current. Well, definitely the BJT is working in the active mode. Definitely, I mean the emitter junction is forward biased, and the collector junction is reverse biased. So previously in the last movie clip, we have learned how to design the BJT device design. But now we would like to switch slightly gears to understand the base current. So to figure out how the base current is flowing, the very first step is what kind of components are there in base current. Okay, so herein you can see that the four components in building up the base current. The base current, base current is definitely this, right? IB, emitter current, and collector current. Okay, so IC is IE plus IB. So previously we have learned the emitter current, but now it's time to learn the base current. So the base current consists of, this base current has what? Yeah, majority carriers supplied for number one, recombination of injected minority carriers in the base. So what is it? Yes, here the hole in the emitter has been injected into the base side, and many electrons would be recombined with injected electrons. So this is number one. Okay. So recombination of injected minority carriers in the base. So since to do recombination with the injected holes, the electron should move. So this electron movement would consist of part of the base current. Second component for the base current is this injection of carriers into the emitter. That means since this is a forward biased junction, right? So many electrons would be injected into the emitter side. So this injection of electrons into the emitter would be another part of the base current. Okay. What about the number three? Reverse saturation current in collector junction, not emitter junction, collector junction. So this collector junction is reverse biased, right? And the reverse saturation current means, here the minority carriers in the N side and another minority carrier in the P side, which is electron herein, that is hole, that is N-type, right? Think about the reverse bias, the PN junction. So the minority carriers near or edge of the depletion layer can be injected, diffused into the depletion layer, and they're gonna be drifted and arrived at the other side. So this saturation current, number three, reverse biased PN junctions, saturation current in the collector junction would be another part of the base current, okay? And the last component for the base current is this recombination in the base emitter uh, depletion region. So, I mean, here, the hole has been injected here into the depletion layer, and electron has been injected into depletion layer, and the recombination event would be happened within the depletion layer between emitter and base. As we have learned, under forward biased PN junction, the holes can be diffused into the N side and electrons can be diffused into the P side. Well, in doing the ideal diode analysis, we have ignored the recombination generation event in the depletion layer. However, in real PN junction diode under forward bias, recombination is serious one, right? Even a small or medium forward biased PN diode, the recombination current is the additional current component, right? So you remember that. So this number four, the recombination current is another part of the base current. Okay, so remember that. So in this slide, if you can summarize how many current components is necessary to build up the base current, then that would be good enough. So I guess that as of now, I guess that you should very well geared up with a PN junction diode theory. Then BJT is, kind of an extension version of PN diode, because two PN diode has been, connected in series. That's all. And on that playground, we are looking at some more, advanced things. Okay. All right. Then now let's move on to the next one. Okay, herein, now it's time to learn three different configurations in building up the BJT-based analog circuit device, analog circuit block. So on the left-hand side, you can see that the very first circuit BJT circuit configuration, the common base circuit configuration. So common means common something, right? So this something here in the base is common for input current as well as for output current. So since BJTs, PNP has three terminals, right? One, two, one, two, three, right? P and P, three terminals. So one of the three terminals should be used as common node. Then we can define, this input voltage and input current, and this voltage difference is defined as output voltage and output current. So one of three should be defined as common. So number one, circuit BJT circuit configuration has used the base as a common. And then the second one, third one is very simple. What about using emitter as a common node? What about using the collector as a common node? Then we can come up with the three different BJT circuit configurations. So that's all. Okay. So now emitter has been used as a common node, and herein the collector has been used as a common node. If I draw the circuit symbol, this one, this is a PNP BJT. So if I'm using a common emitter, so this would be the input node, and that would be the output node. So if I connect a resistor 1, then this would be the common emitter amplifier. Okay. So since I have used the PNP BJT, you may have a chance to use a single stage MOSFET based amplifier. So V in, V out. So since I have used the PMOS has been connected to the pull-up network. Previously, in my previous movie clip, I have briefly introduced the single-stage MOS-based amplifier. So V in, V out. So this is MOS, right? So this is the source. Source is corresponding to the uh, collector for the NPN BJT. So emitter, base, collector, base, emitter. So source side is corresponding to the emitter. Sorry about that. Emitter. Okay. So common emitter circuit configuration for in the version of MOSFET based circuit is this. Okay. And if I instead of MOS, if I'm using PMOS, then you should come up with this circuit configuration. Then this is all MOSFET version. So what if I'm using a BJT? Then this is a PMOS, right? So the counterpart of the PMOS transistor is PNP BJT. The counterpart of the NMOS transistor is NPN BJT transistor. Okay, so in this sense, common emitter has been well used as amplifier circuit. Okay, So on the bottom side, I have brought a output characteristics of common emitter configuration. So output characteristic means output voltage versus output current. Okay. So take a look at the curve for a given, say, input current or base current. How much output current, I mean the collector current, can be observed. So since in the case of IB of 30 microamp, the I sub C value is 10 milliamp. How much gain can you estimate? The beta DC value is IB, IC. So 30 microamp, 10 milli, then 300, right? So this 300, the gain value of 300 is very, very high compared against the MOSFET-based amplifier. Most likely, MOSFET-based one can give us a few tens of gain, value of gain. But BJT-based one is a few hundreds definitely, but even more than that, even 100,000 value can be found and implemented. Okay, so the uh, biasing point or working point would be chosen in this active mode, active region of operation. Okay, active region of operation. Then the emitter to base is forward biased and the base to collector is reverse biased. Just for your information, I guess this part, take a look at the curve. As output voltage increases, output current increases. That means it's kind of a register. From the perspective of a MOSFET, MOSFET is working in linear mode. So in BJT, the BJT is working in a saturation region. So don't be confused a lot. When it comes to the BJT operation point, saturation region is well matched to the linear region of MOSFET. Okay, and saturation mode of MOSFET is well matched to the active region of operation in BJT. Okay, so don't be confused a lot when you are using the word BJT, MOSFET, linear mode, saturation mode. The matching one is linear. The matching word for the linear mode in MOSFET is what? Yes, saturation region. And the matching word for indicating the saturation mode in MOSFET is, yes, active mode in BJT. Okay, all right. So going back to the saturation mode here, okay, take a look at the voltage difference, V sub EC and the V sub EB in a definitely common emitter. Which one is higher? Yeah, V sub EB is higher. So that means if you move the VEB onto the left hand side, you're gonna end up with the VPC, which is VB minus VC is smaller than 0. That means what? Yes, collector junction is forward biased. That means, you know, when the BJT is working as a working in an amplifier circuit, the biasing point should be found in active mode, active region. But in saturation region, since voltage difference is given as follows, so collector junction is even forward biased. Okay, so let's move on to the next one and take a look at here. Emitter junction and collector junction. So emitter should be forward biased and collector should be reverse biased to work in the active mode. But in saturation mode, which is the corresponding word of linear mode in MOSFET, both junction has been forward biased. Then the BJT is working as a kind of resistor. Okay, so here common emitter BJT configuration. Let's think about the output characteristic IC versus V sub. Since we are talking about the PNP, V sub EC, you know, the current is increasing linearly, almost linearly as output voltage increases. But at some point, whatever the output voltage is, the current output current is set and saturated. So that is kind of corresponding to the MOSFET, saturation current can be flown in MOSFET. Okay, so this area, white area, is named as active mode, and this black colored area is named as saturation mode. And to differentiate active from saturation, think about what kind of biasing has been applied for emitter junction and collector junction. Then you can simply understand how the BJT is working. So one more comment for this lecture note is this. Uh, Cutoff means both junctions are shut down, so reverse biased. So no current can be found. Okay, so whatever the output voltage is, emitter to collector voltage has been given a lot, but no current can be observed. Why is that? The both junctions has been shut down and blocked because both are reverse biased. However, if both junction, emitter and collector junctions are forward biased together, then the BJT is working as kind of a resistor. So if we are using cutoff mode and saturation mode together, I mean, alternatively, we can use cutoff afterwards saturation mode, then this BJT can be used as a kind of switch. So this would be the used for the distal logic, okay? However, if your BJT is working in this forward active mode, then your BJT has been used as an amplifier, and that would be good for analog circuit. Okay, so in summary, if BJT's work, you would like to use BJT as a kind of switch for digital logic, you should always think about emitter and collector junction should be both at a time reverse biased or forward biased. It's kind of off and on. However, if you would like to use a BJT as a use a BJT device for analog circuit, I mean you would like to design the amplifier using BJT device, then either emitter junction or collector junction should be forward biased. I mean, one of the junctions, emitter junction or collector junction, should be forward biased. The other of it should be reverse biased. Then your BJT can be well used as an amplifier. Okay, so please remember and refresh your memory with all the contents. And again, I would like to ask you to read out all the sentences in chapter 10, 11, 12. Okay, so see you in the next movie clip. Bye bye.